When working on conformational analysis for cyclohexane derivatives, those molecules containing six-membered rings, it's important to go from the flat representation and turn that into a chair. There are two ways that we can do this. One is we can freehand it using a parallel line method, or we can trace out that cyclohexane. In this case, we have a methyl group on it. So we trace out the six-membered ring and then put on it a CH3 group. As I've traced it out, this ends up being axial, and that is shown here where the CH3 group here is on a bond coming off of the cyclohexane that's parallel to the edge of the paper. This axial methyl group is not the only conformer. If we take this axial methyl cyclohexane and go through a chair flip, we see that the methyl group ends up now in an equatorial position. In a generalized energy diagram showing the energy of these two conformers, here's our axial methyl versus our equatorial methyl, we see that the axial methyl is higher in energy than that of the equatorial methyl by some amount of energy, or delta E. What we want to do is be able to quantify that in a way so that we can determine how close in energy these are, so that we know whether or not it's ever likely to see the axial or the less favorable or higher energy conformer compared to the equatorial in this case, which will be lower in energy. To accomplish this energy estimation, what we need to be able to do is look at all of the atoms that are involved in these molecules and these two different conformers, such that we identify ones that are bumping into one another or generating steric strain. The skeletal representations that we have up here look nice and are a lot less cluttered, but they don't really help us look for those six-atom interactions or steric interactions. So the first step is to draw in all the hydrogen atoms. So you'll notice on the lower set of chairs, now the drawings get quite busy because we've drawn in all these hydrogen atoms. What we want to do though now is look to see, are there any six-atom interactions? And these six-atom interactions need to both be six atoms apart as we count through the backbone, but also pointed at each other. So for instance, if I start at this hydrogen here, you'll notice that it's pointing away from the rest of the molecule. So it is unlikely to be both six atoms and pointing at something. So if we just look at this and I look at things that are near it in space, I can go 1, 2, 3. These are on the same carbon, so not sterically interacting in a way that would adjust the conformer. 1, 2, 3, 4. These are 4 atoms apart, and the whole basis for drawing chairs is such that every one of these is staggered. So we've optimized this for steric interactions. Here's one that seems to be pointing in a similar direction. Let's count that. 1, 2, 3, 4, 5 atoms. Those are 5 atoms apart and therefore not going to be sterically involved. In fact, these are parallel lines, and so they're parallel in space and far enough away that they don't tend to bump into each other. However, if we start looking at this hydrogen here off of the methyl group, we'll call that 1. Again, this carbon is 2, down to this carbon 3, this carbon 4, here's carbon 5. I know that anything attached to this carbon is going to be 6 atoms apart. So this hydrogen down here and this carbon down here are 6 atoms apart, but pointing away from this. Whereas if we go up to here, this hydrogen is 6 atoms apart and they are pointing at each other. So this is a 6-atom interaction. I can do this again, looking for other things that are in space. So I can start 1, 2, 3. Now we'll call this back carbon here 4. That's 5. That doesn't do anything for us. But now if I go to here, this is now a carbon 5. Again, this hydrogen and this carbon are 6 atoms away from our hydrogen of interest, but they're pointing away. But if I circle this one, we'll see that it is also 6 atoms away. And so we end up with 6 atom interactions. So right here, we end up with steric strain from 2 6 atom interactions. So now let's compare that to what we see over with the equatorial methyl. So again, this was our axial, and we'll label this one as our equatorial. If I, again, look at these methyl group protons here, I can go 1, 2, 3, 4, 5. Those are 5 atoms apart. They're just fine. 1, 2, 3, 4, 5. 5 atoms apart. Let's just circle this one and see, because it seems to be axial, so maybe there's something there. 1, 2, 3, 4, 5. 5 atoms apart, not a problem. 1, 2, 3, 4, going to the back carbon, 5 atoms apart. So if we keep extending our counting here, here's carbon 5 atoms away. And then if we get to something that's 6 atoms away, like this end carbon here, this is very far away from this axial projected methyl or proton, and so therefore there are no 6 atom interactions. So qualitatively, we can say that this doesn't suffer from any steric strain, and the axial one on the left has steric strain stemming from these 2 6 atom interactions that we can use our chair conformer with extended diamond lattice drawings and projections to identify. So now if we looked and clean up that picture, what we see here are our 2 6 atom interactions, and I'll just put a little 6 next to those. There are 2 of them, and it turns out that each 6 atom interaction is worth about 1 kilocalorie per mole in terms of steric strain. So 2 times 1 gives us a total of 2 kcal per mole in terms of steric strain. This is positive energy and destabilizing. If we compare that to the equatorial projection, or conformer, excuse me on that, this equatorial conformer has no 6 atom interactions and therefore has 0 kcal per mole coming from steric interactions or 6 atom interactions. So just like we saw on that qualitative energy diagram a few slides ago, this is our lower energy conformer, and this is going to be our most stable chair. One of the things that's really nice about doing conformational analysis on chairs is that you only ever have to draw 2, unlike acyclic conformers where you have to index between all of the different conformational settings, going from fully eclipsed at 0 degrees all the way through 360. Here we're only ever going to be looking at 2 conformers. So let's summarize conformational analysis for 6-membered rings. We use the diamond lattice approach to extend chair structures with substituents. Looking for parallel lines is a great way to do that. And again, like we've talked about before, using color pens and pencils can help you extend those parallel lines throughout your drawing as your chair structures get more interesting. You'll want to draw both left and right-handed chairs because one conformer to do the chair flip will be left-handed, and then when we do the chair flip, it becomes right-handed. Again, we'll use those parallel lines to check our drawings for bond lengths and angles. We'll then use these quality drawings to look for 6 atom interactions. One of the things that you'll see is that when we drew in those dashed lines, you can see new chairs emerging within that structure completed by the dashed lines. Each 6-atom interaction is worth 1 kcalper mole in steric strain. So every time we get these atoms close in space, 6 atoms apart, that provides a little bit of positive energy or lack of stability in those structures. We add up all of the 6-atom interactions to find the total steric strain, and then we can compare that between our two conformers and determine which is going to be our most stable chair and by how much energy. Like with everything that we do, lots and lots of practice is going to help you be successful at this, building this particular skill in 3-dimensional drawing.